Thank you for joining me for more probability and measure. It looks like we're about halfway through the lectures in this course, and today we get to do a great thing. We get to prove the existence and the uniqueness of product measure. We did this already for regular measures, if you recall. We started with the idea of a pre-measure on a ring or a field and extended it to a measure on a sigma field. Now we're going to start with a sigma field, or we're going to start with a measure space. We're going to start with two measurable spaces, product them together, and then figure out now how in the world do we take a set function on rectangles and extend it to a proper measure on a sigma field generated by those rectangles in the product space. Well, we're going to do that today with the help of our friend the integral, and then we're going to go further. We're going to prove Fubini and Tonelli's theorem, which allows us to swap the order of integration for measurable functions, given, of course, the right circumstances and conditions. And lastly, if there's a little bit of time, we will prove the existence of infinite product probability spaces, which is great if you happen to be a statistician and you like to collect data and let that data just tend off to infinity. That and more all coming up in today's lecture, so please stay tuned for that, and let's get into the notes. Welcome back to another lecture of Statistics 571, Probability and Measure. Today we will have the final lecture in Chapter 2 of my notes. And this lecture will discuss the existence and uniqueness of product measure. We're also going to go a little bit further and discuss the famous Fubini Tonelli's theorem, which allows us to swap the order of integrals. Very, very useful in practice if you want to integrate something. We will also... might be a little bit of a long lecture today. We will also get into the idea of infinite products of probability measures, because if you like probability theory or statistics, you're often going to have a sequence of random variables, measurable functions, but random variables, right, n going off to infinity. Well, does it even make sense to have such a thing, right? What if we have an infinite sequence of probability spaces? Can we product them all together into one big infinite product of probability spaces? Turns out the answer is yes, but gotta prove it first, and the proof is actually super annoying. That's going to come at the end of today's lecture. The first thing we need to do is discuss the existence and uniqueness of product measure and get on to Fubini and Tonelli's theorem. So let's do that now. All right, so at the midway point, or in the latter half of the last lecture video, we stated a theorem, but we did not have time to get to the proof of it. The main theorem that we want to prove in today's lecture is the existence and uniqueness of product measure. All right, got that all in the title. So the theorem looks something like this. Let bold x, comma, script x, comma, mu, and bold y, comma, script y, comma, I think nu, yeah, that little v1, that looks like a nu, be sigma finite, so key thing there. Always pay attention to those little things like, oh, they're not just measures, they're sigma finite measure spaces. Pretty sure in some of these books, perhaps Dudley's book, he has like a counterexample of when things go bad when you don't have sigma finiteness, but I don't have that off the top of my head. Anyway, we have two sigma finite measure spaces. And what we're going to do is define pi. Let pi be a set function, not a measure yet, but it's going to be a measure. Right now, we don't know what to measure. It's a set function on the product sigma algebra, such that, yeah, well, it's okay. So it's not exactly a set function on this entire space. Recall that we define this product of these two sigma fields such that it's the sigma field generated by all of the, I guess, rectangles. I should bring that notation back from last time, but we aren't quite there yet. The point is we have a set function, and what this set function does is we'll say such that for an A in my X sigma field and for a B in Y, then pi of A crossed with B is going to be the mu measure of A times the new measure of B. Basically, we're multiplying the length by the height, or the length by the width of our rectangle. If we think of A and B as just being, say, intervals, right, and X and Y being the real line, well, this is just a rectangle, and we're multiplying the length by the width to get the area. Great. But this is a much more general setting. Nevertheless, it's the same intuition. But like I said, this is not a measure yet, it's just a set function. So the theorem claims that then pi extends uniquely to a measure on the product space, the product measure space, which we write as X crossed with Y. Sometimes you see O times as well, and well, I guess on the product measurable space, we have our product X cross Y and our product sigma field script X cross script Y, such that for any E within our sigma field here, X cross Y, then we define, this is the definition or the extension here, is that the measure of set E is going to be defined as a double integral of the indicator function of E for X and Y, and this is d mu X and d nu Y. And equivalently, we show that this is equal to the exact same double integral, but with the order of integration swapped. This is, in some sense, like the baby version of Fubini Tonelli, which allows us to swap the order of integration for measurable functions. But in this case, we're swapping the order of integration for indicator functions. That should actually give you a pretty good hint at how we're going to prove Fubini Tonelli, because if we want to go from an indicator function to a measurable function, probably going to be monotone convergence, but we're not there yet. We need to prove this first, this theorem. Anyway, this is the main theorem, so maybe I'll highlight this in a nice bold yellow. This is what we want to prove. We're not quite there yet, so we need a couple little notation. Let's see what we need. Yeah, no, we don't need that. Yeah, actually, no, we do need R, the set of rectangles. Okay. So we'll say notation. Let script R, I think script R is going to be the collection of rectangles. The collection, the set of sets, the collection of rectangles that is, i.e. For R in script R, we can say that R is going to equal A cross B for some A in sigma field X and B in sigma field Y. So in some sense, what we're saying here is that our set function pi is going to be defined on the collection of all rectangles. And then we're going to extend it to every possible set in the sigma field, in the product sigma field. So we're going to need that notation of script R. And yeah, I think the claim is that the claim that I'm not going to prove. I think I have a footnote that says try it yourself. Pi as a set function is countably additive on the set R, or the collection R of all rectangles. I think it's a semi-ring, if I recall correctly. If you I think it's, yeah, a semi-ring, and if you allow for finite union, then it probably becomes a field, because the entire space x cross y, if x is in sigma field x and y is in sigma field y, then x cross y would be a rectangle in x cross y, the sigma field. Yeah, I should come up with better ways to say this out loud. Nevertheless, the point is that, yeah, actually, I think I have it written right here. I should just be reading my own notes and not trying to think it out in my head. Yeah, which is, we'll say note, including finite unions of rectangles takes R to a field, which we're going to call script A. Probably because they also talk about it as an algebra, and sometimes I swap back and forth between field and algebra, but yeah, in the notes I'm calling it a field, even though it's A, which is the first letter in algebra, so. Anyway, so we have that. That's some of the notation we need. We also need the monotone class theorem. We proved that last time, so I'm just going to state it so that we have it ready to go. I'm not going to prove it again. It's in the previous video. And the monotone class theorem, not monotone convergence, which I keep switching because it's so easy to say the wrong one, even though they're kind of different ideas. But anyway, monotone class theorem says let A be a field, and M be monotone, such that, not sigma, such that A, the field, is contained within our monotone class. Then the sigma field generated by that field by allowing for countable infinite unions is also going to be contained in the monotone class. So again, this theorem, very similar in style to Dynkin pi lambda. So again, yeah, this is very similar in style to Dynkin pi lambda theorem, which says that, you know, if we have a pi system and a lambda system, then the sigma field generated by the pi system is also in the lambda system. In this case, we have a field within a monotone class, and therefore the sigma field generated by that field also in the monotone class. We're going to need that in what's to come, because we are not going to prove, we're still not going to quite prove theorem, the big existence uniqueness theorem yet. We're going to prove a lemma that's going to get us partway there. So this is where we left off from last time. We proved monotone class. I didn't state this lemma yet, so let's state that. So we have a lemma that says, once again, let x, script x, mu, and, well, what else? Y, script y, nu, be finite. Be finite, underline, just to emphasize that, measure spaces. Okay, so now suddenly we've already restricted ourselves a little bit more than that theorem from above. We're working in the finite case. And as often happens, right, we'll start in the finite case, then we'll extend to sigma finite. Anyway, I haven't told you what this lemma is yet. So we have two finite measure spaces, and then we're going to say let, once again, the collection script f, and collection f is going to be all of the subsets of x. Let's try and do that. I don't really like writing bold x and y, but eventually I'm going to use regular capital X and y as random variables, so I'm trying to force myself to use bold x and y, no matter how annoying it is to write. Anyway, so collection f is going to be all of the subsets of x cross y. I guess they can probably be equal, and also just being all of x and y, such that the double integral of the indicator function of x and y d mu x d nu y is equal to, well, the exact same thing, but with the order of integration switched. So what this is saying is f is going to be the collection of all sets that allow us to swap the order of integration when we're dealing with an indicator function. And then that's not the theorem yet. That just is two different statements. So let x and y be finite measure spaces. Let f be this collection. Then the claim is that script x cross script y is contained in f, which means every set in our sigma field allows us to swap the order of integration for these indicator functions, as long as we have a finite measure space, right? And then we're going to extend this later. It's kind of like basically saying that it makes sense. The sets E contained in script F are the ones where it makes sense to like write pi of it, because we want to be able to swap the order of integration, or else it's not a very good product measure, right? Because you could always think of the product. I mean, let's do a little sidebar here, right? We want this space, this measurable space, right, to be kind of equivalent to, in some sense, the flip of it. Let's say y crossed with x, right? We want these to more or less be the same idea, right? If we have a set in one and we kind of like swap the coordinates, the x and y, then it should still make sense in the other one. And so in some sense, what this theorem, this lemma is saying is that all of the sets within our sigma field have a pi, a set function that makes sense, that is like consistent here. So that's basically what we're trying to prove. So how in the world do we do that? Well, proof. First, well, we're going to need to define E. So let E be a rectangle, A cross B, for once again, A is in script X and B is in script Y, which is, just to be clear, E is contained in R. And just to emphasize, remember, the sigma field X cross Y is the sigma field generated by the rectangles. So what I'm saying here is that this guy, right, X cross Y is sigma R. If I take my entire collection of rectangles and I sigmify them, then yeah, we get that sigma field. Okay, then what do we know? Well, if we have a rectangle, we want to show that the rectangles are actually in F, right? Because a priori, we don't even know that we can swap the order of integration for rectangles, let alone for general sets, E. So let's just do that. So in this case, well, we have the double integral of the indicator function for d mu d nu y. And, well, what happens if we write this, if you think about it, is just an integral and of an integral, right? It's two integrals here together. So if we just integrate the inside, right, and recalling that E is a rectangle, so it's A crossed with B, then this simply just becomes, well, the measure of set A times the integral of, well, the indicator function for set B, y d nu y. Right, this is because it's a rectangle. Well, this is the measure of A and nu, the measure of B. Well, luckily, multiplication is commutative, so I can just rewrite this. We'll start over here. I can rewrite this as nu times B, mu A. I can just swap the order of multiplication, sure. And then I can just undo what we did before and say this is nu B integral of A x d mu x, and this will be the double integral once I unmeasure B in some sense and shove it all back into a double integral. But hey, what do you know? Did I do it backwards? No, I did it backwards. That's silly. That's just silly. I was supposed to say, yeah, mu comes out, and then we're supposed to... What in the world did I do backwards here? Mu. Oh no, I'm just being silly. I'm just being silly. I had it all. It's easy to get the mu's and nu's backwards, so I wanted to make sure I didn't do that. Anyway, yeah, it's not that interesting, but it does allow us to show you how you can take this indicator function here for E, you can break it up into the indicator A cross B, which is going to basically give us an indicator B. When we come back, we get our indicator A, and then we're back to our indicator E. Anyway, the main point is, therefore, our rectangles are contained in this collection F. So we know that F is not empty, and it contains all the rectangles, so that's a good start, but we need more. So going a little further, next, for disjoint rectangles, R1, R2, in R, we know that the indicator function for R1 union R2 is going to be the sum of the indicator functions R1 plus indicator R2, right? If we have a disjoint union, we can just take the indicator function of one and add it to the indicator function of the other. And because, okay, then you can just see from above, and the fact that integrals are linear, that F is going to contain finite disjoint unions of rectangles. F contains finite disjoint unions of, we'll just say R for rectangles. Okay, so we're getting a little bit further. And this implies that A, which is the field generated by all of the rectangles, is also going to be in F. And I have a little subnote because it's something I don't really feel like taking the time to prove, but if you go into Dudley's book on real analysis and probability, proposition 3.2.3 states that if you have a semi-ring, like the rectangles are, then the collection of all finite disjoint unions of elements of R is a ring. And furthermore, since X cross Y is also a rectangle, in R we have a field. So I'll say C. Dudley proposition 3.2.3, which basically says that, yeah, if we have a semiring and we have finite disjoint unions of elements of that semiring, we're going to get, well, a ring, but in this case we get a field because we have the entire space omega also in our, I guess, set in R. Anyway, cool. So that means that F contains the field A. But what do we want? Well, we want to go a little bit further. We want to contain the sigma field. So, see, this is how we're stepping up, right? We've got semiring done. We have ring or field done. Now, the next thing we need to do is show that it works for the whole sigma field. So, next, what do? Consider an countably infinite collection. EI, I from 1 to infinity, and of course EI, well, I guess today, of course, EI are going to be in F. So if we know that the infinite union of these things is going to be, then we're good. Oh, but we're going to use monotone class. I forgot what we're doing here. Yeah, we want to use monotone class. So let's consider a countably infinite collection of elements of F. Then, if the EIs increase to E, then monotone convergence, our good friend that's going to get us so far, monoconvergence, we'll say it monotone convergence, says, well, what does it say? It says that the double integral of the indicator function of EI, x, y, d mu x, d nu y, increases to the double integral of indicator function E. D nu x, d mu x, d nu y. And the same holds for the swapping the order of integration, which we'll write out, even though it's, well, a little tedious. Almost there. D nu y, d mu x. Cool. Thus, what do we know? Well, we know that these two things are equal, right? These guys on the left are equal because EI is in F. Therefore, they're the same thing. So these are the exact same two increasing sequences. Therefore, these two guys also have to be equal, right? You have the same increasing sequence. It's got to go to the same number, no matter how you write it down. So the left side's equal. Therefore, the limit on the right are also equal. And what that means is, therefore, E is an element of F. And the same basically holds for going down, yeah. And same holds for EI decreasing to E. All right, and then we're basically done, right? Because therefore, F is a monotone class, and A is contained within F. Therefore, X cross Y, which can be written as sigma A, is contained within F. Cool. So what does this mean? That's QED box. Good stuff. What's this mean? Well, what this means is that if we have two finite measure spaces, then the extension, right, then basically this function pi that we defined way up at the top here, right, pi, which is kind of like the big thing we're trying to do, makes sense in the idea that I can swap the order of integration here for finite measure spaces. Now, what we need to do is we need to actually prove that theorem that we can extend this pi to a measure, both in the finite and in the, I guess, sigma finite cases. So now, on to the next proof, which we'll just say existence and uniqueness of product measure. Sometimes the existence and the exclamation mark is for there exists a unique, so that's just shorthand. Anyway, yeah, let's do that. So, how do we start this? So, first, we consider mu and nu to be finite measures. Okay, and then we're going to do this for finite measures. Then we're going to extend, or we're going to generalize to sigma finite measures. So we start with this, and we have pi is going to be our set function. A cross b is equal to mu a nu b. Remember, we didn't actually show that this measure extends uniquely for finite measure spaces. All we showed above is that we can swap this order of integration for finite measure spaces, which in some sense shows that at least the definition kind of makes sense. Because what we're going to do is say, then we extend to a set function. So, right, we start with pi on rectangles, and then we define pi to an extended version of pi for any e to be the double integral of the indicator function xy d mu x d nu y. Right, so we've just extended this here, and this is any e in the sigma field. So again, the above lemma basically says, well, we can define this set function and the order of integration can be reversed. So I'll put in blue here. Lemma says that this def makes sense, the definition makes sense. And we can swap the order of integration, etc., you know. And this is any e in our sigma field. So now what comes next? Well, integrals are linear. So what does that mean? Well, that means that our set function is finitely additive. Therefore, pi is finitely additive. It's a finitely additive set function. This is basically the same thing I said up here when we talked about the union of two disjoint rectangles, right? That's all. Then monotone convergence leads us to countably additive. So next we apply monotone convergence. Again, greatest theorem ever, right? Apply monotone convergence, and what do we get? Well, we get that pi is countably additive. All right. Thus, it's a measure, right? We have a countably additive set function on a sigma field. It's a measure. Good stuff, right? Therefore, pi is a measure on x cross y. Give it an exclamation mark. We did it. But we don't get a QED box because we only proved it for finite measures. We got to do it for sigma finite measures, so we're not quite done yet, and we actually still have a little bit more to go. So, oh, we never actually proved uniqueness. Okay. Huh. You know, I'm just going to get rid of that. We don't deserve an exclamation mark. Forget that. So, what did we just show? Existence. Hooray. But now we need to show uniqueness. So we'll say to show that pi is unique. That is, that if we start with pi on rectangles and we extend to this definition here, we want to make sure that there's no other way that we can extend a set function on rectangles to something else, right? We want to make sure this extension is unique as we wrote here. So what do we do? Well, let rho be some other set function such that rho of a cross b is equal to, oh, I guess mu, not rho. So again, it coincides with pi on the rectangles. Now we want to show that it has to necessarily coincide with pi on the entire sigma field. How do we do that? Well, we set up a set, a collection, where these two things coincide. So then we say, this is very similar to what we did before with the uniqueness of extension with using Dinkin pi lambda, but we let M, it's going to be a monotone class, hence M, but we don't know that yet, right? E is going to be the E's in X cross Y such that pi of E is equal to rho of E. So these are all the sets where the subsets of our space here, where the two set functions coincide. So the claim is that M is monotone. Let's say a monotone class. Monotone, make sure I get all the O's in the right spot. Class. Okay, well, why? This is because for EI increasing to E, right, which is going to be the union over I from 1 to infinity of the EI sets, then we write E equal to the union I from 1 to infinity of DI, where the DI are disjoint, hence D for disjoint, right? Where D1 is going to be E1 and DI is going to be EI minus EI minus 1. Because they're increasing, these are going to be then disjoint sets. Are disjoint. Okay, and then countable additivity. Yeah. So, oh, no, that's, oh, no, I want this. Yeah, this is still in the little parenthetical comment about the claim. So, by countable additivity, we have that pi of E is equal to rho of E. And we can do the same for EI decreasing. So that's the first thing. And then do same idea for EI decreasing to E. In this case, right, you would have an intersection, but you can still disjointify them and then use, you can kind of go from the other direction. The fact that if you have an intersecting collection of sets, it's kind of like you have a union of their complements that's getting bigger. Anyway, you do the same thing here. You find out that M is monotone. And therefore, well, by monotone class theorem, we have that our sigma field x cross y is contained in M. Thus, therefore, pi is unique on x cross y. For finite measures, we're still not done yet. This is only, so what did we get? Well, we got our existence, we got our uniqueness, but this is for finite measures, for products of finite measure, for finite measure spaces. So now what we need to do is figure out how to extend this to sigma finite. I'm pretty sure, if I recall from reading some of these books, that if you don't have sigma finiteness, then the extension may not be unique, but don't quote me on that. I guess now it's recorded, so unlike a class where I can just say something and it goes off into the ether, now everything's being recorded, so I don't know, that claim might be wrong, but I'm pretty sure there's something that breaks down, if I recall, with like the uniqueness of extension being a problem, where you could have multiple things, but we'll worry about that another day. Let's finish this proof. We say now, let mu and nu be sigma finite measures. And we need a collection. Well, if we have a sigma finite measure, what can we do with it? Well, we can construct a collection of AIs and BIs that are, let this be sigma finite. I'm sure this is an English sentence, right? Let mu and nu be sigma finite measures, and we'll say let AI and BIs be disjoint partitions of x and y respectively, such that, well, the measure of all these sets are finite. So, right, that's what sigma finiteness tells us, and we're going to need to use this fact to get the job done. And what it's basically saying is I can cut up my space into a bunch of pieces. Each of those pieces has finite measure. Even if I add them all together, I get infinite measure. That's okay, as long as I have a bunch of finite measurable pieces. Then, and here come the subscripts, right? We'll say then for any E in an element of the sigma field, the product sigma field, we define sets EIJ to be E intersected with AI cross BJ. So what are we doing here, right? Let's draw a picture, right? Because I like pictures. If this is, let's say, X, and this is Y, right, then what we're basically doing is we're cutting up X into a bunch of pieces. And we're cutting up Y. I'm going to run out of colors pretty soon. We'll use light blue. And we're cutting up y into a bunch of finite pieces with finite measure. And then each of these little spots in here is going to be an AI cross bj. And if I have some set E, right, if this is E, then what we are doing is we're effectively creating the EIJs here by intersecting it with each of these little blocks. This is the visual image, right? We're cutting up X, we're cutting up Y, we're creating all of these little rectangles, and we're going to take E and we're going to slice it up into little rectangles, right? Kind of like cutting one of those big sheet cakes. Just chop it all up, and then you have a nice little picture on your cake. Well, now it's cut up into a bunch of little pieces. It'd be kind of nice if you had a sigma finite cake, I guess, but we'll leave that musing for another day. Anyway, back to the actual math, now that I drew my fun little picture here. From the finite measure case, that is, what we just proved was that we can swap the order of integration for finite measures. So what that means is that I can do the same thing for the EIJs. Because EIJ, right, is going to be E, but in some sense restricted to a rectangle with finite measure, if you think about it like that. Anyway, it's going to take me a second to write this out, but the point is that I can swap the order of integration. That's all I'm writing here. E, ij, x, y, d nu y, d mu x. Cool. Sum over all I and j, right? Now, sum over all I and j, and apply the greatest theorem in the world, monotone convergence. And what do we get? Well, we get that pi e is going to be defined in this way as indicator e xy d mu x d nu y, which equivalently, by monotone convergence, as above, is going to be defined in the same way, x, y, but with the order of integration swapped. So it makes sense. Cool. And this is any E in our sigma field. All right, we're almost there. We just need to show that this, well, furthermore, it's not quite a measure yet. It is going to be a measure. Furthermore, I should just start writing MC for monotone convergence because I have to bring it up so often. Furthermore, monotone convergence implies, as we did above, that pi is countably additive and if pi is countably additive on the entire for any E in the sigma field, therefore pi is a measure on the sigma field. Existence. Boom. Good stuff. And now we just need to show it's unique, right? So how do we show it's unique? Well, that's not so bad, because we kind of did all the legwork already. For any other row such that, as before, rho of A cross B is equal to mu A nu B, right? The fact that it starts the same way, we want to make sure that it has to extend to the same thing. Then we have countable additivity, as usual. countable additivity plus the uniqueness shown for finite measures above, right? We already know that it's unique for finite measures. We just need to know that it's unique for sigma finite measures. So if we put these two things together, what we end up with is that pi of E can be rewritten as the sum over I and j of pi of Eij, right? We have our little cake cutting up here, and we're just going to sum over all the pieces. They're disjoint, that works. Countable additivity for the win. Well, on each of these finite pieces, we know that the measure has to be unique. So we can swap on the finite pieces to rho Eij, cram it all back together by countable additivity, and we get rho of E. And we're done. QED, it's unique. Unique. Give it a little exclamation mark there too, just for fun. All right, cool. So it's a lot of legwork, but what we're basically saying in the end is that, okay, if I have two sigma finite measure spaces, I can cross them, I can create a product space from those two things, and everything makes sense. The measure extends the way you would want it to, which is I start with rectangles and I extend it to the whole sigma field, and I can do that in a way that is well-defined and also unique, right? We don't have any other extensions to worry about. Great. Well, that's good. We're making good time because I want to make sure we got a lot of stuff I wanted to cover. And that's the big existence theorem. We proved it. Now we can move on to Fubini Tonelli. So, right, this allows, basically, we got like two things here. We now know that this measure, pi, exists and is unique, but it also shows us that for indicator functions, if we think of indicator functions as a measurable function, well, for indicator functions, we can swap the order of integration, and it makes sense. Well, it's the two things are equal. What we want to do is we want to do that for any measurable function, and that's what we're going to do next, and that's Fubini and Tonelli's theorem. So the theorem says, let x mu and y nu be sigma finite measure spaces. Okay, and let little f be a function that maps from the product space x cross y into the reals. Be measurable. Be, well, we'll say x cross y measurable. So again, it's going to map sets in R. I guess in this case, I didn't specify it. So it's going to map sets in our sigma field on the reals back into sets of our sigma field in x cross y here, such that either we need one or two conditions. Either one, we have that f is non-negative, or two, we have that f is absolutely integrable. We're going to introduce the idea of like the L1 and LP spaces soon enough, but for now we'll just write it like this. And we're going to write the measure as mu cross nu, because now that we know that pi exists and is unique, well, we can just write it as mu cross nu, and we want this thing to be finite. So basically, we either have non-negative, non-neg, or absolutely integrable, right? One of these things, we need one of these to hold, or both, I guess, but as long as we have one, then the big then says that the integral of f d mu cross nu, remember, this is basically the pi from above, just so you know, can be written as a double integral over f xy d x d y, or mu x nu y. And of course, this can be also written as the same thing where we flip the order of integration. Something that looks like this. Also, not done yet. Also, the function of y, right? If we write f of x, y, d mu x, this is a function of y, and it is y measurable. And similarly, if I integrate out, if I marginalize, right, if I integrate out the y, then this is x measurable. That's actually kind of good, because if we have some kind of joint probability distribution, a joint like a jointly Gaussian random variable or something, I want to be able to marginalize out, integrate over one of the coordinates, and still get something that's still a random variable. And this is what we're basically saying, is that I can integrate out, I can marginalize or integrate out over one of the coordinates, and the thing that's left over as a function of y or x is going to be y or x measurable, respectively. All right. Well, we did most of the legwork already, so this proof is not going to be too long. Let's try it. All right, so what do we do here? Well, as I kind of hinted before, we already know this works for indicator functions, so that's a good starting point. Proof. Well, we have this for indicator functions, which are all non-negative, by the way. Condition number 1. From above. Okay, so we already did this for indicator functions, and then it's going to go directly to simple functions. Therefore, we have the result for simple functions. Sounds like my laundry's ready. Good old basement working, you know? Anyway, we have this result for simple functions as, well, as integrals are linear. And remember, a simple function is just a finite linear combination of indicator functions. So we're done. Well, for simple functions, that is. Yeah, I guess I can write that. Well, do I want to write that out? I don't really want to write that out. Yeah, it's basically that. Okay, I wrote out the equation in my note, but it's just the integral of a finite sum of indicator functions is going to be the integral of a finite sum of indicator functions, but with the order of operation, or the order of integration, swapped. And that just follows directly from what we already did. So now, furthermore, next, I'll say then, applying monotone convergence, greatest theorem forever, as I keep saying, right? Applying monotone convergence to simple functions leads us to non-negative measurable functions. Cool. So yeah, that's the first part, right? That's point number 1 here. We just proved it for non-negative measurable functions by simply just, using monotone convergence. Done. The other one we have to work slightly harder, not that much harder, but like I said, we've basically done all the legwork to get us to this point. So instead, assume that the double integral of the absolute value of f, right, d mu cross nu, our product measure, is finite. Then, well, it's not going to be necessarily positive or negative, but we can write f as the positive bit minus the negative bit. And what we say is kind of the above argument holds for f plus and f minus, because f plus and f minus are both non-negative measurable functions. So, okay. Oh. Yeah, basically the point is that i.e. the double integral of f plus. Oh, I see what I need to do. Okay, not the double integral. The single integral of f plus xy d mu x. So if I integrate over all x, this thing is going to be finite, and this is for almost everywhere. Which basically means for almost every y, this integral will be finite. That is, the set where it isn't finite would have measure 0, would have nu measure 0. And similarly, f plus integrated over y is going to be finite mu almost everywhere. And this would mean, again, for x. And similarly, for f minus. Therefore, the integral of f xy d nu y, the absolute integral, right, can be written as the integral of f plus xy d nu y plus the integral f minus xy d nu y. And this is mu almost everywhere. Therefore, well, we can just write this out without the absolute values. And we can basically, we can subtract, is what we're saying. It makes sense to write this, the subtraction sign. Never thought subtraction would be so hard, right, when you learn it in grade school, or before. Mu almost everywhere. And since we only need finiteness to be almost everywhere for the integral to exist, we can integrate both sides of this with respect to mu. This gets back to, if you recall, there was a theorem we did a couple lectures ago, which basically said if I have two functions that is, I have the left side of this and I have the right side, and the left and the right side, f and g, are going to be equal to each other almost everywhere, then their integrals are equal to each other. So what this is telling us is that, well, left side, this guy, and right side, that guy, are equal to each other almost everywhere. Therefore, I can integrate both sides. So again, we're thinking of this in the sense that we have functions on the left and a function on the right, and I can integrate both of them with respect to mu to get this, basically. F plus xy d nu y d mu x, and I guess minus, I'm running out of room here, minus f minus xy. In this case, it's just equal, right? We're saying that these two integrals, if the functions on the left and right are equal almost everywhere, then the integrals must be equal. And basically, then do same, swapping mu and nu. And we're done, right? QED box. So, yeah, do you buy that? Right? What did we do? Well, the non-negative one was pretty straightforward. If it's non-negative, monotone convergence, done. If it's not non-negative, if it's just absolutely integrable, then we take each piece and we say, well, each piece is non-negative. Therefore, we can consider the integral of this with respect to mu or nu, and that gets us something that is finite almost everywhere with respect to whatever measure we're using, mu or nu. And what that allows us to basically do is to decompose this into the difference of two integrals, or two measurable functions here, which we can then integrate to get the result. So yeah, it's this one's, I guess, maybe the second part's a little bit more subtle than the first part, which is just kind of like monotone convergence done. But yeah, that's mostly like the whole point. And the fact that if I have two functions that are equal almost everywhere, their integrals have to be equal. All right. Yeah, and then there's a little remark I put here, which is, of course, we can do this we did this for two variables, or for two measure spaces, x and y. We could do it for three, x, y, z, via induction, right? Do it for x, y, and z, and then do it for x and y within. So similarly, right, you can extend this idea to a finite product of measure spaces. But what's even cooler is that we can extend this to an infinite product. So by induction, we can extend the above theorems to a finite product of, let's say, capital N measure spaces. I guess sigma finite. I think everything we did this was either finite or sigma finite. So in this lecture, if we have a finite number of sigma finite measure spaces, then we can product them all together. Great. We can swap orders of integration. Great. What about doing it for infinite, countably infinite, or even uncountably infinite products? Well, in general, that can get us into a little bit of trouble. But in the case of products of probability measures, we can do a good job. We can get something that makes sense. And okay, then you might say, well, wait, why do we want products of probability measures? Well, there's two reasons. One is applied side. If we want to do probability or statistics, we might want an infinite collection of random variables. Each of those random variables, in some sense, is a function that can be used, a measurable function that could be used to generate a sigma field, or a measure space. And then we would be interested in the infinite product of those measure spaces. On the other hand, if I need to multiply a bunch of things together, right? And if the entire space has a measure of 1, well, I can multiply 1 by itself forever. And that's going to be a trick. It sounds something kind of stupid, right? But 1 times 1 times 1 times 1 off to infinity is still going to be 1. And that's actually what we need for this last little bit. So this leads us into the final section of today's lecture, which is infinite products of probability spaces. Cool. All right. Yeah, let's see how fast we can get through this. It's the theorem and the proof are actually super annoying. So hopefully you're well caffeinated. I know I am. All right. Notation. We need let omega n fn mu, not mu, p. We're in probability space now, so we'll use p. Pn be, we'll say, n in the natural numbers be a sequence of probability spaces. Hence, finite measure spaces where the probability or the measure of omega n is going to just be 1. Then we define, well, we don't define then, I guess, omega, which is going to be an infinite product, which I'm going to write as ox n from 1 to infinity. So it's omega 1 times omega 2, omega 3, etc. If we take the infinite product of all of these omegas, then this omega, the big product, consists of sequences like little omega I from 1 to infinity, such that omega I probably should have just used n. I think I used both. That's a typo in my notes. Omega I, little omega I is in big omega I. So that's one way to think of an infinite product of probability spaces, would be like a space of sequences, of infinite sequences indexed by the natural numbers. So yeah, I have, for example, if omega n is just the real line, then for all n, then this would be the space of all real valued sequences. So you could think of this as like, well, sequence space, I guess. But then we'd also have to have a measure on top of that. So it's not just any sequence. Well, it is any sequence, I guess, but the sequences would have measures. All right, then let R be the collection, because how in the world are we even going to like get a sigma field out of this? Be a collection of finite dimensional rectangles on in contained within omega. what is a finite dimensional rectangle in an infinite product space? I.e., if R is in this collection script R, then what we can do is we can write R to be an infinite product, O cross, n from 1 to infinity of A, n, for A, n in Fn. So every sigma field, Fn, gives me an An, and I product them all together to get R. But I can't just take any collection. I want this to be a finite dimensional rectangle. And what that means is such that well, I guess I could write it a little bit more mathematically. There exists an n such that for all n greater than or equal, let's just say greater than n, an is equal to omega n. So this is what I mean, is that we're going to define these rectangles such that eventually the things that we're producting together to make this rectangle just become the entire space themselves. So hence finite dimensional. There's only a finite number of n where something interesting is happening, and then the tail of the rectangle product is just a bunch of omegas. It's so yeah, in some sense, all the interesting action is happening in the first capital N products, AIs, I guess ANs. Ugh, sounds horrible when I say it out loud. So we can, I'm not going to, show that R is a semi-ring. And yeah, we denote S to be the field generated by R. So again, R is a semi-ring. It contains finite dimensional rectangles in this infinite product space. S is going to be the field generated by R, so I take my finite rectangles and I finitely union them together. Okay. Next, this is all just notation. We haven't even gotten to the theorem yet. Next, P. We don't even know what P is. It's going to be the product. It's going to be the measure on our infinite dimensional space, but we don't know that yet. P is a set function. I should say we define P to be, we get to choose what it is. We're just going to say P is a set function. Is it the right thing? I don't know. It's going to be the right thing, but a priori, we don't know. It's just a set function on these rectangles such that the measure of a rectangle R is going to be, well, the product n from 1 to infinity of P, N, A, N. So it's really what we did before. It's just that now we have an infinite product. And the nice thing about this being a probability space is that this infinite product is going to converge to something. And it's not going to be 0 or infinity. Well, it could be 0 or infinity, but the point is it doesn't have to be 0 or infinity, which can be any, well, it could be within 0 to infinity, as eventually P A n is equal to P omega n, is equal to 1, and this is n greater than that capital N that I constructed before. So the point is, eventually, the elements in this infinite product are just 1 times itself forever. So we're we can get different things. Then this is where like things get a little bit tricky, right? Because if we have a finite measure space, that's not a probability space. If the measure of omega is less than 1 or greater than 1, then this infinite product will either blow up to infinity or it will shrink to 0. Now, yeah, of course, you can normalize a finite measure space to become a probability space, but this is just the point I'm trying to make, is why we're working with a probability space here. So we can actually write out this infinite product and get something that might be meaningful. All right. So next, define F to be a sigma field on omega. And how do we construct it, right? Because this is the thing, right? We have a bunch of fn's, we have a bunch of sigma fields for each n, but how do we construct a sigma field on the product space? We do it, define F to be a sigma field and such that such that for I probably should have defined these projections first, but that's okay. Such that for projections, which I'm using as var pi, which is kind of looks like a B or a beta that fell over on its face, it's going to be a mapping from omega to omega n. It's a projection where, luckily, we're not actually going to need var pi for a bit. So I can just kind of, it almost looks like a W tilde too. It's kind of a, maybe I should make sure this is connected, even though, yeah, something like that. I'm running out of Greek letters. I'm just running out of Greek letters, Anyway, if we apply this projection to a sequence of omegas, an infinite sequence of omegas in big omega, then we're just taking out the nth observation, or the nth, going back to stats language observation, the nth element of our sequence, omega n. And then, such that for these projections, F is the smallest sigma field such that pi n are measurable for all n. So that's what we do. We construct this sigma field, F, to be the smallest sigma field such that all of these projection mappings are measurable. And that means, right, that the inverse of the projection, taking a point in omega n and unprojecting it into omega, is going to get me a measurable set in omega. That is an element of the sigma field. These are measurable, I should say. This is omega F into omega n F n. So if we want a measurable function, we need to talk about what it's, I kind of said what it's projecting from to anyway, but just to be clear. So, i.e., F contains sets that are of this form, with a n being an element of Fn. So this is actually kind of like how you can, in a sense, you can define sigma fields in terms of measurable functions or measurable random variables, which is very useful if you have, say, when you get to things like martingales and conditional expectations, and you're basically like taking an expectation of one sigma field over another one. It's, yeah. Anyway, oh yeah, little side note. These are sometimes called cylinders. If I can spell that right. Silent. And I just cannot spell. Pretty sure I just wrote that somewhere. Yeah. No, I did spell it right. I just can't read it right. The reason being, right, is if you can imagine it kind of like this. If I have a set AN, then what we're doing is we're unprojecting it up like this. So, right, any point in here would get projected down onto AN. So, hence why they sometimes call these things cylinders. Cylinders, rectangles, all in general measure spaces. Good stuff. Oh yeah, we're going to need one other notion, which is also more notation. And then we're actually going to get to the theorem. And yeah, this is going to be another super long lecture. So sorry, but hopefully you're enjoying this as much as I am. Anyway, the notation is that for... All right, we have one more notation, which is if we have, let's say, a finite product of two measure spaces x and y, like we did last time, like from, well, last time, earlier in this lecture, then and a set in the product sigma field, then and x an element of space x, then what we do is we define a sub x to be a slice of a along x. And that's going to be all of the y in y such that the pair xy is in A. So in this case, if we have some set A, and if we have a point x, then what we're doing is we're slicing it, and the little slice here is going to be A sub x. So that's just notation. And furthermore, yeah. And then we also note that, in fact, AX is going to be an element of the sigma field Y for any X. Seems reasonable. I'm not going to show it because I just want to get to the good stuff. But yeah. This leads us to, well, we're going to need two things. How do we want to do this? I'll write down the theorem, then I'll write down the lemma we're going to use to prove the theorem, then I'm not going to prove the lemma that we're going to use to prove the theorem. Good stuff. Theorem. Existence and uniqueness of infinite product prob measures. Good stuff. And the theorem is very easy to state, very tedious to prove. The theorem says that the set function defined above, P, extends uniquely from R, they're finite rectangles, to F, to a probability measure, I should say, on F. Right, so what that means is that we have a set function P. We defined it on finite rectangles in the infinite product space. And now what we want to do is say that we can extend P to a probability measure on all of F, where F is the sigma field generated by the projections to make the smallest sigma field such that all of the projections are measurable functions. Okay. The way we're going to use to prove this is we're going to use a lemma. And the lemma says, let mu be a finitely additive set function. The key thing is finitely additive set function on a field, which we'll denote as S, script S. Then mu is countably additive, and hence a pre-measure. Countably additive, and this is if and only if we have some condition which is sometimes referred to as like continuity at the origin, if and only if for any sequence of AIs decreasing to the empty set with AI in the field S, then the measure of the AIs goes to 0. So I'm not going to prove that, but you can try it yourself. It's actually not a terribly hard proof. You basically have to disjointify the AIs like we've done multiple times already, and then use properties of series. Like if a series converges to a number, then the summands have to go to 0, and so on. Anyway, you can try that yourself. What we're going to do is we're going to use this to prove the existence and uniqueness of our infinite product probability measures by basically showing that if we have a set function that's finitely additive, then we're going to show this condition, this continuity at the origin condition, the fact that if I have a decreasing sequence, then this thing, the measure is going to go to 0, and then use that to show that it's countably additive. If it's countably additive, now it's a pre-measure. Then we can just use Carathéodory's extension theorem and say, well, if I have a pre-measure on a field, then I can extend it to a measure on a sigma field. All right. So that's the rough outline. Proof. And this is proof of, just to make sure it's clear, it's the proof of that theorem. We're just going to skip the lemma. So we want to extend P from the rectangles to the field S, which is finite union, I guess finite unions of rectangles, and show it makes sense. Right. So it can be shown, which is my way of saying not going to prove it. It can be shown, and yeah, you can find this in Dudley's book, Proposition 821, that any S in this field S can be written as a disjoint union of R's in R. So the point is that S is a field. It's taking R and extending it by including finite unions. And the claim is that for any finite union of rectangles, you can rewrite it as a disjoint finite union of rectangles. So roughly speaking, it's like saying, well, if I have one rectangle and I have another rectangle, then I can basically rewrite this as a finite union of disjoint rectangles. If I draw it like this in 2 dimensions, it's like, well, yeah, that kind of makes sense. You can prove it. Dudley proves it in his book in Proposition 8.2.1. Not going to prove it here, but intuitively, at least it seems like it makes sense, right? Therefore, what this means is that for any S in the field S, what we can do is we can write S as a union I from 1 to k, a finite union of rectangles Ri. In this case, they're disjoint. They can be disjoint, made disjoint. And furthermore, each of these rectangles from the above definition of what it means to be a finite dimensional rectangle can be written as an infinite product, n, from 1 to infinity of a, I, n, where again, where a, I, n is in Fn, and all but a finite number of AIN are equal to omega n, and this is for all n. So the point is that these AINs, no matter what, I guess for all I, that is, eventually, once n gets big enough, and n could be dependent on I, right? But as long as it eventually gets there, right? We only have a finite number of i's from 1 to k. Eventually, all of these AINs just become omegas, and everything kind of stops in some sense. Therefore, we can treat P S as a finite product measure on omega 1 cross omega 2 cross all the way up to omega k. Is that what I want, omega k? I don't think I want. I think k is the wrong index here. Because S is going to be... Oh, I guess it's a finite product measure on... No, because Ri is just going to be a rectangle. No, I don't want k. K is not what we want. We'll just say n, capital N, saying that eventually we don't need, in some sense, any of the further product space, like products. Okay, where were we? We can treat this as a finite product measure. And countably additive on S. Yeah. Okay. By Carathéodory. Right? If P is countably additive, on S, then it extends to a measure on sigma S, which is going to be F in this case. yeah, so I think this maybe is a little bit confusing what I wrote up here. This is just saying that if I throw away all of the additional omegas, right? If I just take all of these and I get rid of them, then what we have is something that's a finite measure, a finite product measure on a finite number of spaces product together, and we're done in some sense. But the problem is that I'm just saying if we're allowed to just throw the rest of these away, but for a specific set S, we might need more or fewer omegas to make this work, right? Because this S is specifically telling us how many omegas we need to product together. And for a different S, we might need more omegas. Now, in a supremum sense, we need all the omegas product together. For any given S, we only need a finite number of omegas. So that's the subtlety here. Because then the point is that Carr-Theodori says that if P is countably additive on all of S, then it extends to a measure. So what we do is, therefore, we use the above lemma to show that for some ai, I from 1 to infinity, decreasing ai, or decreasing such that there exists an epsilon greater than 0, such that, terrible English sentence, but that's okay, such that the probability measure of ai is greater than epsilon for all I, then the infinite intersection of the AIs, what we're limiting to, is not going to be empty. So we're going to use the lemma inverse. That's what the rest of this entire proof is going to be, which is doing this lemma, but in some sense backwards. The lemma says, well, mu is countably additive if and only if for any decreasing sequence, sequence decreasing to the empty set, then the measure has to go to the empty set, or to 0, sorry. The measure of the AIs converges to 0. What we're doing here is we're saying if we have any decreasing sequence such that the measure doesn't go to 0, then this is contrapositive. If measure doesn't go to 0, then the limit cannot be the empty set, right? Contrapositive, right? It's A, then B, or not B, then not A, right? If we get the logic there. Anyway, let's see if we can get through this before my computer and camera time out, because this is super long. Okay, let's do this. Let P naught be just P on S. Okay. For n greater than or equal to 1, we define omega n to be the infinite product for m greater than n of omega m. So this is like a tail product. We're only taking the m's that are greater than n, a infinite tail product, right? And we have Sn, the disjoint unions of rectangles from omega n, and we need that, and we need one more thing, which is Pn, which is P restricted to Sn. So in some sense, when I have a superscript n, I'm saying consider only the tail product, right? Where I start at n+1 and go off to infinity. Because what we're ultimately going to do is we're going to take the finite bit, 1 through n, and then we're going to take the tail and kind of like deal with the tail separately. All right. What else do we need? For any E contained in omega, the infinite product space, and a collection of points, x1 through xn, in omega 1 cross omega n, we define En. Again, it's going to be a tail event, x1 through xn, and this thing is going to be the collection of sequences xm m greater than n in the tail space omega n, such that the entire xm sequence, m greater than or equal to 1, is in E. So basically what we're doing is we're fixing the first endpoints of our sequence, and then we're taking all of the tail sequences, such that the entire sequence lies in this set E. Okay, little abstract, but we're going to get there. Yeah, we're going to get there. All right, from the above. So now for any E in omega, not in omega, well, yes, but for any element of this field S, there exists an n, well, greater than 0, of course, such that E can be written as F crossed with the infinite product little n greater than capital N of omega n. This is what we said before, which is every element of this field only has a finite number of interesting pieces, and then the rest of it is going to be all of this omega junk, where it's just like, okay, and then it's just omega all the way down. Omega's off to infinity. And this is for some F contained in O cross n from 1 to n of omega n. So F is the finite piece of E, hence F, right? F is the finite piece, and then we have our trivial tail sequence here, the product of the omega n's. Therefore, let's take some tea. Therefore, F can be decomposed into the union I from 1 to k, Fi, which is the union I from 1 to k of the product. And now this product is no longer infinite. It's n from 1 to capital N of Fin. So again, F can be broken up into a finite product of a finite union of disjoint rectangles, and each of those is made up of a finite number of product of pieces product together, where Fin is an element of Fn. So yeah, F is a finite union of n-dimensional rectangles. Good stuff. Yeah. For any choice of m less than n and x1 through xm, we have em of x1 through xm, and this thing is going to be some g crossed with omega capital N, the tail sequence, the tail product, for g, and g here is, so we basically cut off the first 1 through m, and then, 1 through m. Maybe I'm thinking I should have started this at m plus 1. Let me double check. Yeah, it should be actually m plus 1. We cut off the first m, and then we're truncating this at capital N as well. So g is going to be a union over all I such that xi is in fi, fin, and then we product together for n from, this should be, I think, m plus 1 to n of the fin. Okay, what is g? G is just a way of writing em. So if we write em as we did above as like a bunch of tail sequences, what we're saying is we have the g bits, which is the interesting finite piece, and then we have omega n, which is just the extra omega junk where we just don't care about that anymore. Therefore, this guy, em, is going to be an L, or actually for n, I should write that. Yeah, I'll just write it the way I have it. En x1 through xn is an element of Sn. What does that mean? That means that Pn is defined on Sn. Cool. Feels a little dissatisfying, right? When you go through all of this just to show that, oh yeah, and then P makes sense defined, that is tail Pn makes sense on tail Sn because the tail ENs lie within tail Sn, and we can decompose them in this finite way. So, great. Now let's do some Fubini Tonelli. All right, well, my audio kind of died there. The video battery looks like it's getting low. So yeah, those are all signs that I should probably wrap up this lecture. We're almost done, actually. Well, we are and we aren't. Next is, okay, so this is what we just got to. Hooray, Pn is defined. Via the Fubini-Tonelli theorem, what we have is that P, the measure of set E, right, can be written as the indicator function of dp1 crossed with ... crossed with dpn crossed with dp capital N, or capital N, in superscript n. So the point is we've got the finite bits here, and then we've got the tail here. And we know that this tail measure makes sense. It's defined correctly. So now we have a finite product of measures. We can Fubini-Tonelli it, and we can swap the order. And what we get is Pn of the measure of this En tail sequence, x1 through xn, and this set, this probability, this function, right, of x1 through xn is integrated with respect to P1. through Pn, which are just the finite, or not the finite, the probability measures that we started with. Good. Okay. Now, returning to the AI from above. At this point, they're like, well, wait, what are the AIs? Like, I don't even remember after we did all this crazy stuff. The AIs are this, decreasing. These are the AIs. Right? This is what we want. It's this decreasing sequence such that the measure of each of these is greater than epsilon. Okay, so returning to those AIs, we have AI, I from 1 to infinity, decreasing. Remember, these are in the infinite product space, such that P of AI is greater than, greater than epsilon, which is greater than 0. Then we define f I to be x1 in omega 1 such that p1 of a I1 x1 is greater than epsilon over 2. What in the world is that? Okay, this is the set that is set of x1s such that the tail sequences have measure greater than epsilon over 2. So it's basically all of the starting points for a sequence, an infinite sequence, such that if we take the measure of the infinite sequence bit, if we throw away the first bit and we take the measure of the infinite sequence bit with respect to the measure P1 defined on those infinite tail sequences, then that thing has at least measure of epsilon over 2. So in some sense, it's like if I have, I think my screen recording is about to time out. Anyway, the point is we're constructing this set Fi on omega 1 so that if I start a sequence at an x1 here, then it's going to go to an x2, an x3, and so on. And the measure of this whole bit, this infinite measure here, this would be like the AI1 of x1. And the measure of this thing has to be greater than epsilon over 2. And this is for each I, where the AIs, right, are the decreasing sequence. I told you, this proof is crazy, but I really wanted to do it, so I'm going to suffer through this, and you can do it at home as well. I wonder if anyone's still watching at this point. You are in my mind, at least. All right, so using the Fubini Tonelli integral formula from above, that is, we want to apply this thing up here to A with E equal to AI. What we get is that epsilon has to be less than the measure of AI. That's by assumption. I guess I should be saying the set function P of AI, because we haven't actually shown it's a measure yet. It's just a set function that is finitely additive, and we want to show that it's countably additive and thus can be extended to a measure. But yeah, just to be a little pedantic. Anyway, using that above integral formula, we get something that looks like this. dp1x1. Okay. Well, now what we can do is this is over all of omega, I guess omega 1, right? This is over omega 1. Well, we can break this up into two pieces by, well, I guess linearity, countable additivity, whatever you... The fact is we can break this up into fi of p1 ai1 x1 dp1 x1. And we can add to that omega 1 minus fi. And then I'm just going to, same thing. I'm not going to rewrite it. The point is we have an fi here and we have an omega fi there. Why is that interesting? Well, because this can be bounded above by the p1 measure of the set fi plus epsilon over 2. Why is that the case? Well, if we're on omega minus fi, we have this thing here is basically less than or equal to, right? How did we define fi? Fi is the space where this thing, this p1, ai1, is greater than epsilon, which means if we're not on that space, the best we could possibly do, the biggest we could possibly get is an epsilon over 2, and the measure of omega 1 fi can be no greater than 1. So it's just epsilon over 2. On the other hand, for this first bit, what we're basically saying is, well, this thing has to be less than or equal to 1 because it's a probability measure. And if we just replace it with 1, it just becomes the measure of the whole set fi. So again, these are reasons why we need this to be a probability measure, or else we can't argue this way. Right, so that's all we need to say for that. Therefore, if we subtract epsilon over 2 from both sides, we get that p1 fi is greater than, or equal to, I guess. Greater than or equal to, doesn't really matter. I don't particularly care. Epsilon over 2. I guess it's greater than because it's the first one is strict. It's just the second one that's not strict. All right, so we have that. Yeah. Oh yeah, that's right. So we have that that's true, and this is for all I, and the AIs are decreasing. So the FIs are decreasing. Do you believe it? Do you remember what FI is, right? FI is like a piece of AI. It's like we're taking AI and we're taking off just the omega 1 piece. So if AIs are decreasing, then each of their like constituent parts has to be decreasing. And FI is kind of like a piece of it. All right, furthermore, and P1 is, well, it's a probability measure, so it's a countably additive prob measure on omega 1 F1. What's that mean? Well, what that means is that if we take the infinite intersection I from 1 to infinity of Fi, and this thing is going to be the integral of the indicator function of the infinite intersection, this is terrible to write this in the subscript, but we'll do it anyway, of dp1 Okay, that's just, it's a measure, probability measure. Well, intersection becomes infimum because the indicator function of a bunch of intersections can be thought of as the infimum over all the indicator functions of the fi dp1. Now we can swap integral and infimum. Why can we do that? Monotone convergence, right? This is going to be integral indicator function dp1. This is just going to be the inf over all of the p1 fi's, and this has to be greater than epsilon over 2. Greater than or equal to epsilon over 2, I guess, because we have an infimum. Yep, so again, monotone convergence for the win, as always. Great, so what does that mean? Well, it means that the measure of this infinite intersection is not 0, therefore this thing is not empty. This is because, again, countably additive probability measure. So what that implies, again, is that if we have this infinite intersection, if the fi is decreased to the empty set, then the measure would have to decrease to 0. In this case, the measure is not decreasing to 0, therefore the infinite intersection cannot be the empty set. All right. Well, what do you think we're going to do next? We're going to do the exact same thing, but now we're going to do it for omega 2. Next, what we do is we fix. What we know is it's not empty, right? This is important. This thing is not empty. So we can fix a y1 in the infinite intersection I from 1 to omega, or infinity, of fi. Don't care what it is. I just need to know that it exists, and there exists at least a y1 somewhere in there, so that I can pick it. Pick whatever one I want. Then we define gi, and gi is going to look a lot like fi, but it's going to be defined as the second bit, omega 2. This is really like the worst proof ever, but I really wanted to include it. y1, x2. At least hopefully you're getting some intuition out of like what's actually going on here. Because when you read this for the first time, it's just like, what in the world are they doing? Anyway, the idea is that now we're taking a subset of omega 2 such that our sequence, y1 is fixed in omega 1, x2 is allowed to vary in omega 2, and then the measure of everything that comes from omega 3 onward has to be at least epsilon over 4. Whew. All right. So by same argument as above, i.e. what we just did for the fi's, we can do them for the gi's, and if we do it for the gi's, what we end up with is that pi of gi, oh, my battery's dying too, look at that, pi of gi is greater than epsilon over 4. And this implies that the infinite intersection by the same argument of the gi's is not empty. So, pick y2 in the infinite intersection of the gi's. We can do that. It's not empty. And now we're basically done. In the off chance that my camera dies, or my mic dies, or my computer dies. Everything's dying. But not the proof. The proof will continue on, right? So, continue via induction to construct a sequence yi I from 1 to infinity yi in omega I such that the tail measure of a I n y1 through yn is greater than epsilon over 2 to the n, and this is for all I. So all we need to do is show that yi is in aj, and this is for all j. Mainly, we want to show the intersection of all the AJs is not empty. That's what we've been trying to do this whole time. And if we have something that exists in all the AJs, its infinite intersection can't be empty. Right, so what do we do? For each J, select an NJ such that, has to be large enough, such that x1 through x nj is in the product omega 1, typo there, omega nj, such that, infinite recursive sequence of such that's, this set, x1 through xnj, is equal to either the empty set or the kind of trivial infinite product of the omega n's. This is possible, which is doable, as aj is an element of S, our field. Thus, oh yeah, we definitely lost the camera. That's all right. We've got one line left to go. Thus, for n large enough, what do we have? Make sure my other mic is still on so that you can still hear me, or else it's just going to be writing, right? Thus, for n large enough, we have that a, j, n, y1, yn is going to equal omega n. Since this sequence y1 and so on, I guess to infinity, is in aj, for all j, we get to the conclusion, which is the infinite intersection of the aj's is not empty. Therefore, P is countably additive. On S. And we can extend it. Can be uniquely extended to all of F. We did it. QED. Only an hour or 2 hours and 16 minutes in. Good stuff, right? Anyway, that's the point. That's what we were trying to get to. Is that, like, what did we do here? The whole crazy derivation here all comes back to the idea that we want to show that there exists something that lies in all of the AJs that are decreasing, and so that their infinite intersection is not empty. And it took all of this craziness to do it. we constructed these Fs, which are kind of like the finite pieces of these AJs, and we kind of like tacked them all together, showed that they're decreasing, they're non-empty, and their measure is in such a way that we can sum it all up, hence the epsilon over the 2 to the n bits, right? Because then if we can, I don't think I actually wrote that, but the point of the epsilon over, no, I never actually told you what the point of epsilon over 2 to the n is, right? I mean, you can imagine it in your head, right? You can sum that up and it just becomes epsilon, right? But more or less the point is that it's decreasing, but it will always be non-zero, which means that all of these Fs are always going to be non-empty, which means I can pick Ys in each of the Fs and I can construct this big sequence. Yeah, I think that's pretty good for today. Apologies for having such an extremely long lecture. I thought it would be interesting to include this proof. It's quite a long, tedious proof, but you know what? Yeah, still feel good for including it. And next time, yeah, we'll be moving into the next section, which is we need to set up a bunch of background material so that we can talk about probability theory. I want to do law of large numbers, central limit theorem, ergodic theorem. To get there, we're going to need some tools like, well, the theory of LP spaces, Holder's inequality, Minkowski's inequality, etc., etc. And that's what we'll be doing next time. See you there.